so we just looked at basically three cases where, what does it look like when we say limit as x approaches c of f of x equals L? There's basically three different ways that can look. So I can have a function with a hole in it. The limit allows me to talk about what happens at the hole. If I can have a hole with a displaced value, and I can still talk about what takes place at the hole without regard to the displaced value. Or if I just have a function that doesn't have a hole, then the limit and the function value are just the same thing. So now my question to you is, what kind of a graph, what would it look like if the limit as x approaches c of f of x was not L? These all have a limit. So we say the limit exists and it's L. All right, what would it look like if the limit, if it wasn't L? How would that look? So take a pause, think about that for a bit, and come back. All right, so did you get an idea what you think the limit, what it might look like if the limit is not L? So there's a couple of different ways that could happen, but I'm going to show you sort of the main one, and then we'll expand out from there. So the main idea of what it would look like if the limit was not L is that if I had the function coming up to a hole, but then the function jumps. So it's sort of like this jump, but instead it jumps and like all the points are up there. All right, so all of this is happening at a certain value c. These are supposed to be perfectly vertically aligned. If they're not vertically aligned, just tilt your phone a little bit so they are. All right, so in this case, what happens if we try to define the limit? So let's say you tried to put the limit and say, well, this one where the hole is the limit. Then all somebody would have to do is say, let's do an epsilon band here, an epsilon band, for example, that is half the distance between the two holes. All right. Then what kind of delta band could I use? Well, if I use any delta band at all, so remember the delta band, since its absolute value of x minus c is less than delta, all right, that delta band is always going to include points over here on the left, but also points over here on the right. Now, we can have a small delta band and keep the points on the left inside the epsilon band, but we cannot keep the points from the right inside the epsilon band. Now, if you had a huge epsilon band that included both of them, then yes, all the points would be included in the epsilon band for this delta band. But the definition requires for any epsilon greater than 0. So if we want to say the limit is not L, all we have to do is come up with one epsilon that it doesn't work for. So the statement is for every epsilon, this stuff has to happen. So if we can come up with any one epsilon where this doesn't happen, then that limit is not L. So and that's what happens if we try to define the limit here. And you can probably see the same thing if I try to define the limit up here. Then again, if I take a small epsilon band, then my delta band is going to include points here on the right that are in the epsilon band, but it's also going to include points over here that are not in the epsilon band. All right, and the same thing, of course, happens if I try to take the limit somewhere in the middle. All somebody has to do is say, well, we're going to make the epsilon band be this bit in the middle, have this be your epsilon band, and then you're not going to have any points inside the epsilon band. So the way the definition works, in these cases, no matter what epsilon you choose, you can get a delta that will land the points in the epsilon band. In this case, for some epsilons, specifically the ones that are smaller than this gap, you cannot find a delta that will include both of them. All right, so in this case, what we say about the limit as x approaches c of f of x, it's not this L, let's call these L's 1, 2, and 3. It's not this L1, it's not this L2, it's not this L3. It's not anything. So we say it does not exist. Does not exist. All right? But there is something we can talk about with this picture that is important and is going to help us to talk about limits more. So let's come back to this and label these L1 and L2. So what we can say about the function at c is that if we ignore the parts on the right and we only take x's that are coming in from the left, then the limit is L1. So what we say is the limit from the left of f of x is L1. And we write that, are you ready for this? The limit as x approaches c, and we put a little exponent minus right there, from the left of f of x equals L1. And we'll look at some specific examples of this coming up. All right, so now as we're coming in from the right, the values approach this value up here. So we're going to say the limit from the right of f of x is L2. And we write limit as x approaches c, and we put a little plus sign of f of x equals L2. So this is saying the limit as x approaches c from the left of f of x is L1. The limit as x approaches c from the right of f of x is L2. What it means is, as the x values come from the left, the y value we come to is L1. As the x values come from the right to c, the y value that we approach is L2. So we'll talk a little bit more mathematically about what exactly that means in the next video.